Right now, the star outside your window looks finished. Fixed. The same size today that it was yesterday, the same size it will be tomorrow. That impression has always been wrong. The Sun is partway through a multi-billion-year process of change, and NASA can already describe, in specific and dated terms, most of what happens next. This is not about a flare or a storm, the kind of sudden violence a previous episode on this channel already covered. This is about the Sun's actual life story, the one written into its hydrogen and helium, unfolding over billions of years instead of seconds. It is the countdown a previous episode promised was already running underneath every other thing in this solar system, including you. Start with what the Sun is right now, because right now turns out to be a more specific position than it feels. NASA describes the Sun in plain terms, a 4.5 billion-year-old yellow dwarf star, a hot glowing ball of hydrogen and helium. 4.5 billion years is difficult to hold in your head honestly. It is longer than there has been a solid crust on this planet. It is longer than there has been liquid water sitting anywhere nearby. Than halfway through its lifetime. It is expected to last another 5 billion years or so before it becomes what astronomers call a white dwarf, a small, dense, cooling ember of a star. Add those two verified numbers together, the 4.5 billion years already spent and the roughly 5 billion still ahead, and the Sun's entire working lifetime comes out to somewhere close to 10 billion years, not far off the age of the universe itself, which is measured at about 13.8 billion years old. Halfway. Not near the start of the story. Not near the end of inside the calm, stable, almost boring middle third of a story that began long before you and will not finish until long after every trace of you is gone. Every second of that middle age is powered by the same basic process. Deep in the Sun's core, hydrogen nuclei fuse into helium, releasing the energy that eventually reaches you as sunlight. NASA's own description of the Sun keeps it simple on purpose, a huge ball of hydrogen and helium held together by its own gravity. Nothing exotic. No hidden mechanism. Just an enormous, steady furnace, running on a fuel supply large enough to last billions of years, and slowly using it up whether anyone is watching or not. That calm is not permanent, and it is not even as calm as it currently feels. The Sun has been steadily growing brighter for its entire existence, and that slow brightening is not cosmetic. There is a specific physical threshold attached to it. Researchers describe an increase of just 6% in the solar constant, the amount of sunlight reaching Earth, as enough to trigger a runaway greenhouse effect. A hotter atmosphere holds more water vapor. More trapped heat evaporates more ocean, which traps more heat again, a feedback loop with only one direction once it starts. Current climate modeling puts the onset of that runaway on the order of 600 million years from now. That is an estimate, not a fixed date, and the exact threshold is genuinely hard to pin down, sensitive to atmospheric details that are difficult to model. But the direction is not in doubt. Long before the Sun does anything dramatic, this quieter brightening alone is enough to end this planet's era of liquid water on the surface. Looks, from any casual glance, exactly like it does today. Notice what kind of ending that actually is. Not a single afternoon. Not a headline event anyone alive could witness starting and finishing. It is a slope, not a cliff, a gradual tightening of a feedback loop that took the Sun most of its life to wind up, and that once it starts running in earnest, does not stop running until the oceans it began with are gone. The reason a number like that is so hard to pin down is not carelessness. It is that the actual mechanism, how clouds respond, radiate away before the feedback truly runs away, is genuinely difficult to calculate. The direction, though, is not in question. The dramatic part comes later, and NASA can date it with real specificity. When the Sun approaches its red giant phase, some 6 billion years from now, it will run out of fuel in its core. Deep inside, the hydrogen that has powered it for its entire life finally runs low. Fusion in the core slows. Without enough outward pressure from that fusion to hold against its own gravity, the core contracts, burning helium instead of hydrogen. The outer layers of the Sun respond to that internal shift by expanding dramatically, swelling the star to many times its current size. What that expansion means for the planets nearby is not evenly distributed, and there is an actual named source on the specifics. Dimitri Veras, an astronomer at the University of Warwick, put it directly: I am confident that the Sun will swallow Mercury and Venus, and not Mars. But the fate of the Earth, which resides in between, is less clear. Read that carefully. confident about 2 planets and admitting real uncertainty about a third, and that third planet is the one you are currently standing on. Recent modeling suggests Earth probably will not make it out intact, dragged inward by drag from the Sun's expanded outer atmosphere, even as the Sun's shrinking mass would otherwise let Earth's orbit drift outward instead. The two effects compete, and which one wins is still being modeled rather than settled. That is a genuinely strange position for a planet to be in. Not condemned outright, the way Mercury and Venus are. Sitting exactly on the boundary between two competing forces, one trying to drag it inward toward the expanding star, the other trying to release it outward as the star loses mass. Whichever calculation eventually wins, that argument will not change anything about how any of this plays out for anyone alive today. But it does mean that even a question this large, will this planet still exist, does not currently have a settled answer. Some questions about the deep future stay open not because nobody has looked, but because the physics itself is close enough to balance that small details decide the outcome. Here is the detail that tends to surprise people, because it runs in the opposite direction from everything else in this episode. While the Sun's expanding outer layers are busy possibly swallowing Mercury and Venus, the Sun is also losing mass, throwing off about half its total mass over the course of this transformation. Losing mass means losing gravitational grip. Every planet that survives the encounter responds to that weaker grip by drifting into a wider, lazier orbit. According to NASA, the outer planets' orbits will drift outward, settling twice as far from the Sun as they sit today. Neptune specifically, currently about 30 times the Earth-Sun distance, is expected to eventually hike out to around 60 times that distance. So the same event that ends the inner solar system as a going concern hands the outer solar system more room than it has ever had. Nothing about that outward drift makes Neptune, or Uranus, or Saturn, or Jupiter more habitable in any meaningful sense. It just means the geometry of this entire system is not fixed, not even at the scale of planetary orbits, not even over the full lifetime of the star holding it together. Eventually, after casting off its outer layers, what remains of the Sun settles into that white dwarf NASA mentioned earlier. Small, dense, no longer fusing anything, radiating away the last of its stored heat for a span of time that makes the rest of this episode look brief by comparison. None of this is a warning about anything imminent. Even the nearer of these endings sits hundreds of millions of years away, longer than our own species has existed by an enormous margin. Nobody alive today, and nobody who will ever be born, has any reason to plan around any of it. This is simply what current modeling of the Sun's evolution says happens to the star you are currently orbiting, described in the same plane, specific terms used for anything else that has already been measured and estimated. Here is what is actually worth sitting with. You exist during a very specific, narrow window inside a much longer story. The Sun is a little past its own halfway point. The quiet climate shift that ends this planet's habitability arrives measured in hundreds of millions of years. The dramatic swelling that may or may not end the planet itself arrives measured in billions more after that. And through all of it, the outer solar system quietly gains room to move. Every one of those timelines is already implied by ordinary stellar physics. We only recently became the kind of species capable of doing the math. Think about how recent that capability actually is. For nearly all of human history, the Sun was simply the thing that came up every morning, a fixed point nobody thought to question. It took the accumulated work of generations of astronomers and physicists, building instruments capable of measuring starlight down to fractions of a degree, before anyone could say with real confidence what a star like this one is made of, how long it. That knowledge is barely a century old. The Sun has been running this same program for 4.5 billion years regardless of whether anyone understood it, and it will keep running it for billions more regardless of whether anyone remains to watch. So here is the honest question for the comments. If you knew, with real confidence, that you were living inside the stable middle third of a roughly 10 billion year story, would that change anything about how you spend the years you actually have, or does a number that large stop meaning anything at all past a certain point? We have spent this episode on a star slowly changing over billions of years. Next time, we turn to a much stranger kind of quiet. NASA's tally of confirmed worlds beyond this solar system has now passed 6,000, and not one of them has ever answered back. That silence turns out to be one of the most serious open questions in all of astronomy, and next episode is about exactly why.